another connection, and a connection that I hope is actually going to be relatively easy for you guys to do. And that is, we're now going to look at what happens when you take, again, some aldehyde or ketone, and again, this works for both aldehydes and ketones, but instead of adding an oxygen diol, we're going to add a sulfur-based diol. So this is where that logic of chemistry comes in instead of memorizing. Oh, they took my periodic table now. I gotta get my periodic table back. You don't see a periodic table anymore, do you? There used to be one over there and over there. Darn, they were gonna fall. All right, I'll get them back. If you look at a periodic table, tell me something about the behavior of sulfur. Tell me something about the behavior of sulfur based on where it falls in the periodic table. Same column as oxygen. So that means it's going to behave much like oxygen. So if I give you that molecule and that reaction to occur, I hope that it is very logical to all of you that the answer to this question is going to be, again, to make this acetal, but to make it with a sulfur instead. And in organic chemistry, we use the term bio to represent sulfur. So thioacetal is the term that you will see to describe this kind of molecule. Okay? So you make them exactly the same way that you make a regular oxygen-based acetal. The importance of the thioacetal is if you then add to it hydrogen gas and something that we call Raney nickel. Right? Raney is the man's name, and nickel is the catalyst. And the shorthand way that we usually write this is R-A-N-I. And again, I just show you that because it may show up on a standardized exam. It's so specific, it's probably wrong, but just in case. Raney nickel is nickel catalyst, and it's a little different from the catalyst we generally use in hydrogenation. Raney nickel is the nickel catalyst, and what they do is they stick the hydrogen to the surface of the catalyst before you add it to the reaction mixture. So in most of these reactions, you take the catalyst, you take the organic molecule, you mix them together, you bubble hydrogen through. With Raney nickel, you stick the hydrogen to the surface first. That makes it a lot more easily transferred. Remember what happens in these kinds of reactions. The alkene or the molecule that's reacting comes down, comes in contact with the surface, and then hydrogen is transferred. But if I add my catalyst and the hydrogen is already sticking to it, whenever that alkene or molecule comes down, the hydrogen is already there. So Raney nickel is much more efficient, much more effective at transferring hydrogen. Now, I'm never going to ask you that on an exam, but again, it's just this idea I have that you should never see something without having some understanding of what it's all about. This is one of those magic things, right? And it really works. It works beautifully. You make this dithiol, this thioacetal, you treat it with hydrogen and Raney nickel, and what happens is the Raney nickel replaces dicyano compound first, and then treat it with rainy nickel and hydrogen, and you can get exactly the same place. So both of these can be used interchangeably. Both of these can be used interchangeably. Tell me why you might want to use one over the other. Tell me why. Mercury is actually pretty bad for you, so that's a really good point. That's an excellent point. I'll buy that. Beyond the healthcare risk, which is nothing small, right? Nothing to laugh at. Beyond the healthcare risk, what else might be going on? That's a really good thought, my dear friend. You can't selectively reduce. They both reduce the carbonyl group. But again, you're speaking the right way, Mark. It is used as a protecting. That's again a very good comment. It is used as a protecting group, but then we're taking it all off at the end, right? So both of these reactions are getting us from the same starting material to the same final point. And yet there might be a time when you might selectively choose to use one over the other. Rainy nickel is much more efficient. I agree with that, but it's also a lot more expensive, and it's 2 steps versus 1 step. 2 steps versus 1 step, that's a concern, right? All of you chemical engineers know this idea of atom economy, where that's the big thing in green chemical engineering these days. If you start with X number of atoms, you want to end up with X number of atoms being used. You don't want excess atoms that aren't being used and have to be disposed of somehow. Tell me more. Well, not quite there, Corey. That's a good thought, right? The side does block the side chain, but you, dear partner, are on the right track. The problem is, think about all the organic chemistry you know, and all the functional groups you know that react with acid. You can protonate alcohols, you can protonate other things, you can protonate double bonds. The problem with Clemenson is because it requires a very strong acid, it's always going to have competing side reactions. Right? So exactly what Corey said, if there are other groups present, you've got to worry about will they react with other groups. And so that does become a concern, right? Clemenson is still very viable, very valuable, but you got to worry about that. Great question. The rainy nickel uses acid in catalytic amounts simply to allow for this to happen. Right? A few drops of acid will work. In the Clemenson case, it is a lot of strong concentrated acid. Very common. Okay? Okay? Alright, so adding sulfur is much like adding oxygen. That you should all keep in the back of your mind. Almost anything you can do with oxygen, you can do with sulfur because they're in the same group of the periodic table, which means they have the same outer shell electron configuration. And if they have the same outer shell electron configuration, it means that they're going to behave in the same way. You can. You can reverse diacetyl fast, just like you can reverse oxygen acetyl. And a lot of textbooks, you'll see the reverse done with mercury, because mercury and sulfur have a high affinity with each other. If any of you are interested in public health and those kinds of areas, one of the ways we clean up mercury spills or toxic mercury waste is to just spill sulfur all over it. And the sulfur just absorbs the mercury to form mercury sulfide, and you can clean it up quickly. So a lot of times you'll see sulfur used instead of A+, but you can reverse it either way. No, that's a very good question, Chris. There are ways to oxidize it, but it's not something that we're going to be interested in doing. The big thing about putting the sulfurs there is to remove them to get rid of the carbonyl compound. You can always oxidize sulfur to get sulfur oxide, right? That's another big thing. But yeah, in this case, it's not going to get us where we want to go. Okay? All right, so what happens, my friend, if instead of using an oxygen nucleophile, we now use a nitrogen nucleophile? So let's look at what happens when I take unstarted aldehyde or ketone, and let's add to it ammonia of related to Todd's question earlier. Why does this have to be a catalytic amount of protons? Why do you need an acid catalyst here? Or it's very logical, Camille. Very good. So the purpose of the acid catalyst is what it's always been, to protonate the carbonyl to make it far more susceptible to nucleophilic attack, right? None of us are going to argue about that because there's no room for argument. That is absolutely true. But more than ever in this case, the amount of acid has to be catalytic. It has to be a few drops of acid for the whole reaction. Why is that so important, Luke? Very good. Because if you use an excess of acid, what is the most basic molecule in this mixture? Ammonia. And so if you use an excess of acid, if you don't do it catalytically, if you just throw in a lot of acid, what happens is the NH3 react with acid to form NH4+, as Luke just said. And once you take the ammonium ion, you destroy the nucleophilicity, right? There's no longer a lone pair of electrons. Without a lone pair of electrons, this reaction can't happen. So, you need acid, you need to protonate the carbonyl group to get this whole thing started, but you don't want so much acid around that you're going to screw with the nucleophilicity of nitrogen. So the first step, again, is going to be protonation of the carbonyl group. What happens next? What happens next? And you all know this, go ahead. The nitrogen acts as a nucleophile, right? It's the same thing that happens in the case of oxygen. We protonate, and then nucleophilic attack occurs. When nucleophilic attack occurs, I end up with OH. My nitrogen has donated electrons. It has 4 bonds now and becomes positively charged. If it's giving up some of its electrons, it becomes positively charged. And then something acting as a base comes in and removes the proton. Something acting as a base comes in, removes the proton, and the result of that is you get a molecule that looks like this. Now again, this is another one of those many molecules that I've told you about that has a lot of biochemical significance. And so many of you in your futures are going to hear about molecules called carbenolamines. Carbenolamines are important intermediates in many metabolic pathways. That is actually called a carbenolamine. O-L for alcohol, amine for amine. Okay? Carbenolamines look like that. Notice, make a comparison. Look at the comparison between that and the addition of oxygen as a nucleophile. They're identical, guys. You protonate the carbonyl, you add the nucleophile, you lose the proton. They are the same first 3 steps. What happens next in this relatively acidic solution? What happens next? Protonation. What gets protonated? Oxygen and nitrogen. Very good. You can protonate either one. Nitrogen actually preferentially gets protonated because it handles the positive charge better. But when you protonate the nitrogen, you're going back to where you came from. You're reversing the equilibrium. So as Jimmy said, the next logical step, if I want to keep moving forward, is to protonate the oxygen. So the next logical step is to protonate the oxygen. And when I protonate the oxygen, I get this guy. Get it?
Does it sound like this is where you recognize there are multiple parts in the form or multiple functions where you show what you want?
That's a really good point, my friend. It's a little different because in this picture, you're looking at multiple products. Here we're looking at all of these things are possible. So I really want you to realize that the nitrogen is actually protonated preferentially here, but we're only looking at the one that's moving us forward. Yeah, we're just focusing on forward direction. Absolutely. What happens next? Right, so now I've protonated this oxygen. I've got a great You should all look at that. Well, now you should look at that and say, oh, I know the answer, right? Before today, you should have looked at that and said, absolutely not. No way in the world. But why, Brian? Resonance, right? The neighboring nitrogen has the ability to donate electrons. Now again, Brian told me that answer about 25 minutes ago. Nothing is different. These are step by step, exactly the same. Step by step, exactly the same as they were with the oxygen compound. What happens next? What happens next? Good thought, because here's where the thing gets different. Very good. So if you make the comparison to the oxygen case, at this stage of the game, another alcohol came in and attacked. So another ammonia comes in and attacks. It's a really good thought. And again, it's not right, but I sincerely mean that is extremely logical, Jay. Now the difference, this is where you need to start, right? This is where you need to make yourself, tell yourself, this is the difference. The difference is, in this case, you have an acidic proton that is very easy to remove. In this case, with the oxygen, we have an OR group there, and there was no proton that you could remove. So in this case, what happens is exactly what Jay said, something acting at the base, and Jay said ammonia, and it's a lot of ammonia, so we'll do it just because he said it. You can simply write the letter B. Something acting at the base comes in and removes that proton. And let me just pull this down for a second because I don't want to erase any of this. And I will lift this up in a minute and we'll go back into column. Okay? Something comes in at the base, removes that proton, and gives you this molecule. This is the only point of difference. This is a really stable molecule. Every atom has an octet. Nothing has charge. This is a stable intermediate. So unlike the oxygen case, where second nuclear pop had to add to give you a stable product, in the case of ammonia, only one nitrogen molecule adds, and you get this. Now I cannot tell you, I can tell you I've probably taught 20,000 kids over my lifetime here at least. And most people don't think about this enough and think you have to memorize two distinctly different mechanisms. They're identical until the last step. And the only reason they change at the last step is in the case of nitrogen, you have a removable proton. And in the case of oxygen, you don't. Okay? Again, extremely important molecule in biochemistry. This molecule is called an imine, not amine, but imine with an I. And this molecule is also commonly called a Schiff base, after the man who discovered it. And it really does play a lot of role in biochemistry. Okay? So imines and Schiff bases are intermediates in a lot of metabolic pathways. No, you do not have to be able to make them. Now, hard question. What do you think happens? What do you think happens if you use a primary amine instead of ammonia? Now look at everything that's on the board. That's a very beautiful piece of work out there. Look at all of that and tell me, what do you think happens if I were to use a primary amine instead of ammonia? That's exactly right. The only thing that changes is the structure of the final product. In the final product, instead of an H on the nitrogen, you would have an R group. And the reason that is so very, very important, we're going to do a couple of examples in a few minutes, is if you look at this, this is the only place where you are removing the proton. So in order to get this stable molecule, you must have a replaceable proton here. You must have a replaceable proton here. You also remove a proton here. Right? So when you look at this reaction, from beginning to end, you need to have two protons that have to be biological ketone if you're a chemical engineer, and you can treat this molecule with ammonia and H plus, and the result of this is you can get this shift base. No problem. Or you can treat this molecule with methylamine and H plus. And the result of this is you can get this shift base. No problem. You can take benzaldehyde and you can react benzaldehyde with ammonia and H plus. And the result of this is you can get this imine. Or you can take benzaldehyde and you can react it with isopropylamine and H plus. And you can get this product. Okay? So nitrogen nucleophiles add identically until the very end. And at the very end, there is a subtle difference. And that subtle difference is due to the removable acidic hydrogen. Now, I'm going to expect you all to have that down today. We've done a lot. We have to do one more thing. But I want you to just realize it's not as overwhelming as it may seem. It's not as difficult as it may seem. It's all about that removable hydrogen. Okay? And so the last thing I want to show you, and again, I want to keep this up here as much as possible, is let's look at what happens when you take that same type of aldehyde or ketone. Okay? So this time, let's do it with acetone. And let's add to acetone a secondary amine with a proton. And again, it's not going to hurt anybody to hear this for about the 50th time. Okay? This is about the 1 millionth time I've said. What's the first step of this reaction? Protonation of the carbonyl oxygen. Why? To make it more susceptible to nucleophilic attack, right? The first step is exactly the same as it was here. That's why I kind of want you to see these side by side. So the first step is protonation of the carbonyl. The first step here was protonation of the carbonyl. What's the next step of this reaction? Exactly right, Tiff. The cap of the nucleophile, in this case diethylamine, on the carbonyl carbon. Oh, I did that the wrong way, guys. I apologize profusely. I attacked the wrong carbonyl carbon. You do indeed need to protonate the carbonyl. You need to protonate the carbonyl. I am so sorry. To give you and because nitrogen has donated its electron, it becomes positively charged, right? Look, it's the exact same step there. Exact same step. Nothing has changed. And what happens next? What happens next? What happened here? Base removes the proton. Guess what? Here, base removes the proton. Same step. Same step. Okay? And again, let me lift this up. What happens next? Oxygen picks up a proton to make a good leaving group. That's going to happen here too. My oxygen is going to pick up a proton to make that good leaving group. To make that good leaving group. And what happens, again, my dear friends, once we make that good leaving groups do exactly what you paid them to do. They leave. And so here's this good leaving group, and it is gone. Okay? There's that good leaving group, and it's gone. It has left the building. is a good cation. And again, why is it such a good cation? Because I can write a resonance structure. I can write a resonance structure, and I'm giving you a big hint of what's to come by how I'm drawing this now. Here. And now, if I'm on a roll, I'm going to slow down a few minutes and make sure you're all with me. And again, if you look at what I've drawn right above what we did with ammonia, everything is identical. Everything is identical. But now I have a problem. Because look on the lower board. What was the final step? Removement of the acidic proton to form a stable neutral product. So when you use ammonia or a primary amine, the last step is removal of an acidic proton to form a stable, uncharged, neutral product. Guess what? You can't do it there because there is no acidic proton on this nitrogen. So something else has to happen, and what actually happens is base comes in and removes one of these protons. Remember, we call these the alpha protons. They're next to the carbon-nitrogen double bond. It takes away one of these protons, forms a double bond, and drops the electrons there. And so what you end up with is here's that newly formed double bond to here, and you end up with a structure that looks like this. So with secondary amines, another big biochemical term, you end up with molecules called enamine. Enamine. And this word, depending on the textbook you use, can be spelled in either of two ways. It can be spelled either with the E in or with the E out. They're both okay, depending on the book you use, but I just want you to see them both, right? And enamine is a molecule with an alkene and an amine in it. An enamine. All right? The last question of the week, looking at all of this, is really quite impressive. Right? If this stuff starts to make sense to you guys, I'm hoping that over the weekend it will start to make sense to all of you guys. If this stuff starts to make sense to you guys, you'll be really in good shape. The last question of the day. What happens when you use a tertiary amine? What happens when you use a tertiary amine? Go back. You're thinking smart, my dear friend, but go way, way, way back. Brilliant answer. So tertiary amines don't give you a product, right? Because you're good if you can get that far. But right here, what's the first thing that has to happen to stabilize this? You got to get rid of the positive charge on the nitrogen. And if this was a tertiary amine, you would have N, R, with a positive charge, and you can't get rid of it. There's no acidic proton. So when you use a tertiary amine, it adds and then it simply leaves, right? So the tertiary amine is like shaking hands, and then once the handshake is done, I form the bond, the handshake is done, I leave. I'm now stable without it. Maybe I bang into it again, and I form the bond again, and then I leave, and I'm stable without it. You can't add tertiary amine. The very first step is non-productive because there is no acidic hydrogen that can be removed to stabilize the adduct. Right? Adduct is just a fancy word we use when you bring two molecules together, ADD-UCT, if you've never heard of it before. There's no way you can stabilize the adduct there because there isn't an acidic proton. So the governing factor in all of these reactions is where is the acidic proton removed? Where do you take it from, Chris?
So it happens.
With the tertiary amine?
Where it is active.
Oh yeah, absolutely, Gerhard. That's a really good point. better nucleophiles than ammonia, right? The 3 electron donating R groups increase electron density on the nitrogen and make tertiary amines great nucleophiles. So it adds, there's no argument that it adds. But once it adds, the handshake, once you do the handshake, if it doesn't get anything productive, it simply leaves again. Absolutely, Gary. It definitely adds. Right. They are not acidic enough. The CH3 protons are not acidic enough. The only reason that you can actually remove these protons in this case is because when you remove these protons in this case, right, these are not really acidic protons, but you remove them here, you end up isolating a very stable molecule. And that's the driving force of being able to remove this relatively non-acidic proton, is you get a stable molecule that can be isolated. Yes, great question. All of these reactions are reversible. All of these reactions are reversible. Because just like you can protonate a nitrogen or an oxygen, you can deprotonate a nitrogen or oxygen. All of these reactions are also equilibrium-based. That means they have forward and reverse reactions. So that's a really good question. Let me just show you a quick example of that. An example of that would be something like this. And this is, again, a good mechanism for you guys to practice after you've had your holiday picnic. You can take a molecule like this, and you can treat this with acid, water, and heat. And if you take that molecule and treat it with acid, water, and heat, you can go back to this guy and this guy. Right? And again, what happens? The first step is protonate the nitrogen to make it more susceptible to nucleophilic attack. Water attacks the carbon. So again, it's extremely logical if you think your way through. Protonate the thing with the lone pair of electrons, attack the most positive species. Yes, there are. No, good question. If you start with an unsymmetrical ketone, like methyl ethyl ketone, you favor the more substituted double bond. You favor the more substituted double bond when you make the enamine because it is simply thermodynamically more stable. Great question. So if you start with ethyl methyl ketone, you're going to remove the hydrogen from the CH2, not from the methyl. Very, very, very good question. Thermodynamic stability wins out. All right? All right, everybody have a good weekend, and I will see you all next